talk this morning, I think Chris gave a very beautiful kind of meta talk about doing research and being a researcher and things like that. So over the course of the day, we have a mix of talks planned, and some of them will be like that, and some of them will be about specific research areas that we expect that you'll see over the course of the week at ICFP or FSCD or the associated workshops. And like, if this is your first time coming to a conference, then like me personally, I feel like generally I follow along for like maybe the first 5 minutes of the talk, maybe 10 minutes when it's like an ICFP talk or something like that, but I don't know too much about the area of. So our goal with these kinds of talks today is to give you a little bit of a hook, so maybe you'll get a few minutes further. But it's normal to be pretty lost for most talks, like that's fine, that's what I think. So we've got some of those planned in this session. And the first one will be by Conor McBride, who will be making a few different types of observations. Thanks, Conor.
Something like that. Okay. Well, I'm going to make a few remarks about the programming language, Frank, which is something that I've been working on and off for a very long time. Sort of story interacts with mine in various ways. So I'm not going to be totally technical. I'm going to try and make it a bit human. And I'm going to start with a few Fred's remarks about my mentor, who was my father, Fred McBride. I'm afraid, not only am I Oxbridge educated, white, middle class, etc., I also fell into the cauldron when I was a baby. Mine is a peculiar journey. So the 5th of February 1944 was when the Colossus, the first electronic computer, ran its first program, and by an outrageous coincidence, it's also the day my father was born. He was a bright kid. His father was a bus conductor. My dad counted up the money at a frighteningly early age and all of that sort of thing. Did well at school, went to university to study engineering, was sponsored by Belfast Shipyard. But at the time, ICL had their offices on the same site. And he used to sneak in at lunchtime to ask questions about this newfangled computing device they had there. And by the time he was through his undergraduate degree, this engineering stuff was not for him. He'd already switched to applied mathematics because the applied mathematics department owned the computer at the university. And the shipyard was still paying. And then he said he wanted to do a PhD. And he said, well, we're not going to sponsor that. Go on. But that didn't put him off. He did a PhD. And sometime in about 1969, he added a recognizable pattern matching notation to Lisp, round about the same time as the case expression was being invented in Edinburgh by Rob Burstall, who ended up being my PhD supervisor. So I have pattern matching from two different directions. Here's an early example. Let's see if we can focus on this. This is from my father's thesis. It's a pattern matching implementation of symbolic differentiation, another program which has played quite a large role in my life. But more on that another time. Yes?
Is this a program syntax, what you just did, or was it like formal notation?
Well, it was a Lisp meta notation which got translated into good old-fashioned S expressions to be, when you were typing it into the newfangled teletype to interact with the read-eval print loop. Wonderful stuff. So imagine how I felt when finally pattern matching went mainstream on the 2nd of June 2014, when a real proper app development language finally acknowledged the value of some types and added pattern matching to Swift. I was really looking forward to phoning my dad up to tell him that he'd finally won. what happened was that my brother phoned me up to tell me he was dead. So that's a sad story. But yes, he died. He died only 4 years after his own father, and that was 3 years ago. So I'd better kind of keep an eye on arithmetic progressions. So I don't have a photograph of him, but let's put it this way: the morgue attendant didn't have any problems recognizing me. Anyway, my father basically conned me into doing lots of hacking when I was a kid. But you should be reassured, my elder brother escaped completely. He did a PhD in historical linguistics. He keeps chickens. But I did not. So I ported pattern matching to Lisp to Turbo Pascal when I was 15, and then the next year I was conned again into rewriting the whole thing in C and having some fun with that. I'll show you a bit of the kind of fun that we had. This is not the syntax. This is a translation of the sort of program I was writing into fake Haskell. Basically, imagine if you were allowed nonlinear patterns in Haskell, and you were also allowed to use the append symbol on the left-hand side. And with the usual, actually we often think of pattern matching as being a kind of algebraic thing, right? But it's often interpreted operationally as, is there a matching substitution? Which doesn't quite fit exactly with the algebraic viewpoint if you start doing things like this. So the idea was to sort of straightforwardly, in your face, is X in the list? Well, how could it be in the list? If the list was like that, then it would be. And if it wasn't, then it wouldn't. So how does such a thing work? Well, trying to match with this kind of pattern involves effects of choice and failure. We're used to matching like going wrong and triggering an alternative match on the next line of a program, but how about a match that can go wrong and trigger other candidate matches on the same line of a program? So we've got something, an append symbol, which at every step of the list you're matching, the append could happen at the beginning, or it could happen one element further along, or so on. So there's some choice effects happening, not on the right-hand side of the program, where we're used to effects happening, but on the left-hand side of the program, where we're trying even just to figure out what the matching substitution is. So that was fun. And then I extended it a bit more so that I could start writing programs like this, where the idea is we're going to write functions that take lists of words or something and give back parse trees. This time, what happens is that any kind of failure effects that happen whilst evaluating the expressions on the right-hand side can backtrack as far as the most recent choice point, which might well be inside the pattern match. So it became, fun just to take the pretty printer and write it backwards to get the parser. It doesn't always work, of course. Terribly inefficient if you just split the list up without paying attention to how much of the input the different parsers want to consume. But it's an awful lot of fun to think, yeah, actually, programming could be as obvious as that. And isn't that something to strive for, to make our programming notations just as directly and clearly meaningful as possible? I got conned again a few years later when some of my dad's mates in the education business got the funding to see how some 9-year-olds would react if they got lots of sort of laptops and had one laptop per child computing activities. And one of the things they wanted to do was programming logo on these laptops. And then they discovered that the laptops weren't as compatible as they might have been, and they couldn't find a version of logo which ran on these machines. So I got conned into manufacturing one. But I didn't do as good a job as Seymour Pert at commenting out interesting bits of Lisp when implementing logo. So funny things would happen. So for example, well, you could write this sort of traditional logo programs, how you draw a square of a given side. And you could also write, functional programs like this one, which squares a number. Okay? And then maybe you issue the command square 10, and what happens is that you get a very small square. If you type squat 10, then it prints out 100. Now the question is, what happens if you type squat square 10? Well, I'll show you what happens. You get this picture. You can see that it's all gone dark. Why is it not dark? It's the automatics of trying to create too many overlays. So you can see that the line that went from 0 up to 10i, we didn't tell the 9-year-olds they were on the complex plane. Has been squared to become the line from 0 to -100. And then the point at the top is the image of 10 plus 10i, right? That's going to be 200i. And you can see that, for example, well, all of the angles have been preserved except at the origin, where the angle's been doubled in the usual kind of rules for config mapping. And so what on earth is going on? Well, so first of all, why did I write just squat 10, right? Why are there no brackets? Well, it's because in logo notation, there's a clear distinction between doing and being. If you want to talk about the thing as a value, you put a colon in front of it in a logo identifier. And with no colon on the front, an identifier is being used as a verb. So horrendously unreadable Polish notations make perfect sense, although sensible people do actually put parentheses in. But the other thing with square 10 is that, the white space doesn't quite mean what you're used to. Or does it? What white space means in this language is to use the thing in the function position to contextualize in some way the evaluation of the argument. And you're used to, perhaps, the boring call-by-value way of contextualizing the evaluation of the argument, which is to twiddle your thumbs until the argument delivers a value, and then do what you are going to do with that value afterwards. And in a call-by-need language, though, you might be used to slightly more amusing co-routining between the function and the argument. So there's always been kind of funny kinds of contextualization of which kind of ordinary mathematical function application is just one corner case. And we might well consider what else we might do. And one thing that happens in this dialect of logo is that a function changes the meaning of the drawing side effects that happen during the evaluation of the argument. Just straightforwardly, as a coordinate transformation. Any function that you can do to a point, you can just do it to a drawing. What fun we had, you know, homing the turtle and then saying, you know, go forwards by 2 pi, and then you know, applying the exponential function to that. So it gets a very small circular dot, which we could then multiply by a large enough number that we can see it. So there's something funny going on. This language also allowed you to contextualize arguments by catching failures. You could also bind variables. Something in a function position, its role could just be to bind a bunch of variables that occur free in the argument. So that was fun. In fact, ordinary pattern matching just becomes a function that tries to compute an environment. And it might also fail. So then you have this interplay between failure and choice, and between binding and environment. And just for fun, we added a thing which allowed you to say, well, if we've got multiple contexts and we want to use them all for the same expression, you can just gang them up. So you can say, draw this picture the normal way, but also upside down and backwards. And that was quite useful from a visualization point of view. When my father died, we found on his desk a draft of a high school mathematics textbook using this as the visualization language, which at some stage leaked to the world. Anyway, many years later, I was in one of Paul Levy's many call-by-push value tutorials where he said repeatedly, a value is, a computation does, and then he would draw this diagram illustrating adjunctions. One of the weird, or a particular adjunction, one of the things that was big trouble during my PhD was that I would write things on the board for Rod Burstall, and he would look confused. And then he would suddenly say, oh, adjunctions, and I wouldn't know what he meant. So I'm beginning to get there. So in call-by-push value, you have this separation between values, which are, and computations, which do, and they're connected by this adjunction between, so values are interpreted as things in the category of sets of functions, like the normal world we live in, but the computations which do effects are interpreted in the category of algebras for the monad that characterizes the effect. Never mind what that means technically. Basically what's going on is that the rightward direction of the adjunction is saying to be is to do, as Socrates might have put it. And then the other direction is saying to do is to be, as Sartre might have put it. At this point I could never help but think of the Kurt Vonnegut punchline, which is, to quote Frank Sinatra, Paul would give these tutorials and he would say, a value is, a computation does, and I would just start laughing. So that gave me one of those crucial things, right? That gave me the foundational joke for a research program. Having found the joke, I could then begin studying. As to how to achieve a kind of mellow, smooth interleaving of doing and being, and possibly the kind of co-routining that would enable strangers in the night to exchange glances. So I should hurry up. Right. So Frank separates doing and being. So here's a piece of Frank code at last. So I should explain that all of the words are nouns, and The curly braces, that's another joke. They indicate they're suspenders. Braces are suspenders. That's the translation guide for you. Right, so crucially, this if operation takes a Boolean and two suspended computations of type X, and it decides which one of them to actually do. So it's not like Logo, where you put extra punctuation on the things that are being. It's that if that the bang is nullery doing. It's been suggested, and I actually agree, that we should probably just use C syntax for this and be done with it. Yeah, so crucially, the point is that we don't want to evaluate both branches of the if and then choose which value. We want to choose which computation, so that, for example, this program doesn't have unintended consequences. The color scheme is purely coincidental. Right. So a little bit more. So here's an example of an actual effectful Frank program. Frank organizes effects by interfaces, and an interface says what commands a program can do without saying anything about what they mean. So here I've just written, just as a syntactic convenience, reverse function application, so that I can write something a bit like a case expression. And then I define this next operation. This is like plus plus in C. You know the C++ joke? What does C++ mean? Add to C, return original value. They walked into that one, didn't they? Classic cell phone. And, yeah, so this is the thing that, in the type it says, well, I'm going to compute an int, but I need the ability to manipulate state of type int. So this thing in orange square brackets is an ability. I think I even have a caption. Yes, it's an ability. It's the ability that's needed to do the operation. And then when we actually do next, we get the value, and on the fly we increment the state and we return the original value of the state. Okay? And then here's the thing that actually gives this is one way of giving meaning to those stateful operations. So this might be called an effect handler by some people, but it's just a thing that looks like a function in Frank. So state takes two arguments, and on the second argument, it is also willing to handle state requests. And then the pattern matching program explains what to do if there's a value received. That's to say, if the second argument process gives a value, I should explain. Pattern variables, right, patterns without orange chevrons match only values. So when I just write a plain old X, I mean I'll accept any value, but certainly not other requests. So this says when you get a value, stop giving back that value. But if you receive either a get request or a put request, then keep handling, calling for the thing after the arrow is the resumption. This K is bound by the pattern, and it captures what the argument computation is going to do once it gets the result of the command. So you can see in the case of the get command, we call the resumption with the state that has been received, and otherwise, when we get a put command, we update the state, and we call the resumption just with a trivial acknowledgement. So then if we write something like map, this is a fairly typical definition of map for functions, we can put these pieces together. We can kick off a state at 0 and map the operation it does next each time, and we can map it across unit, 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 and we'll get 0, 1, 2. So there's something, so I should explain that the orange chevrons document an ability. An adjustment. An adjustment is how a type explains what's different about the permissions for the inputs in this position. So that adjustment says, in this input position, I'm listening for state requests. Right. And crucially, you'll notice the type of map, and actually earlier the type we had for if, said nothing whatsoever about effects. Indeed, an early rejection of a talk proposal on Frank received a comment from a reviewer that the abstract claims Frank has effect polymorphism, but I can see no sign of it whatsoever. And I thought, that's right. Because what we're saying is not what the effects have to be, but only how they change. So the type of map says, whatever effects are permitted for the whole of the map operation are passed on unchanged to the function that is allowed to, that runs at each element. So that's an effect polymorphic map without even trying. So yeah, it's time I stopped. So I'll ask what's not being said. I've said most of this already. So the crucial thing, I guess, there was even, yes, I said that too. I'll just skip to one last propaganda slide. I'm not going to give you typing rules, just the kind of philosophy for constructing typing rules, which is that types are ideological. Rather than looking at programs to figure out what types they have, much better to look at types to figure out what programs are allowed to be. And we invent appropriate disciplines for typing to push into programs. So, in my philosophy, well, I don't know if it's as grand as a philosophy, you synthesize types only for uses of things whose types you already know. So that there's already a type telling you how this gets used. And everything else gets checked. Same goes for types, same goes for effects. Phenomenological, like, let's look at it to see what it does, type systems considered harmful. I better stop there.
Okay, so remember that you can ask questions either by asking a question or writing a question or typing it in Slack.
I'm hoping I've given Derek plenty of material for later.
Where's Slack channels for people?
Gabriel?
ICFPconference.slash.com.
So it is a general channel?
No, it's the PNW02 McBride channel. But you can ask on the general channel, but now it's too late, so you should ask in person.
Okay, so one question was, when you have choice points in patterns, is that not an advertisement for Prolog?
Yeah. And it's, what peculiar prejudice? So, see, I can take advantage of the fact that this is an anonymous question. Yeah, but why not? I mean, so you need to know that the choices happen, right? But we often write programs where we signal by maybe having a return type that's a list of something, that there's some choice going on. I'm not in favor of kind of completely hidden, unadvertised effects. If you're willing to say, so in particular, a pattern which contains some kind of ambiguity to it might well have choice effects, and it's up to the context to explain how those choice effects should be dealt with, what the search strategy should be. So the point is that the type should say what the deal is, and the deal might well be the Prolog deal. Why not? Might be appropriate sometimes.
Any other spoken questions?
Can you explain the usefulness of all of this as if I were a 5-year-old?
Go to your room. Well, writing programs that have effects, or writing programs, well, okay, so I can explain it to you like you're a 15-year-old. You want to be sure that the programs which are running inside your computer with this camera pointing at you don't see what you're doing in your room unless their type tells you that's one of the things they get up to. I mean, yeah, just advertising what the deal is, which kinds of behaviors are permitted to a program, and also, we also have the property that Frank programs must handle all and only the effects they advertise in the adjustments, which means they don't intercept commands unless they say they're going to, which might also have some value. So it's just about being a bit more precise about what the deal is, about which things programs are allowed to do in a way that's trustable, and also that might help you write programs to the same interface, which are given different meanings in different situations. So it gives you more compositionality. I'm not sure 5-year-olds care about compositionality, except like Lego and stuff. But if you liked it for Lego when you were 5, you might like it for other stuff.
Okay, so we're running a little bit behind, so we should stop questions there, but if you have questions, you should.